Thank you. Yeah, so this is trying to work with Stefan Wagner, who is hiding in the back. So I'm going to first explain a bit what B-trees are. I think most of the audience is very much familiar with them, but just in case to get everyone on board. So B-trees are search trees, which means they are rooted trees, and inside the nodes of the tree we store keys. Keys have values. The point is that, well, keys that are positioned to the left are smaller than keys that are positioned to the right. And one of the nice properties is that B-trees are balanced, which means that the distance from the root to the leaf is the same for any leaf. Okay. They have a sort of a branching parameter, so we look at B-trees of order 2m plus 1. What this basically means is that a node cannot contain more than 2m keys, and you'll see how this looks like on the next slide. And I restrict for this talk to the case m equals 1 for most of it. Yeah, so you can construct B-trees with an insertion algorithm, and then there's two models how you can generate your keys. So the first one is what Jesper already used in the previous talk. You just assume that your keys are sampled from a continuous probability distribution. But what will be quite handy for this talk is to assume that it comes from a uniform permutation. And there's no difference between the two. Okay, so let's take this permutation here, and let's build a B-tree of order 3. So we start by inserting the first key. It just gets into a node. There's nothing to be done. Now the next key, it's smaller, so it goes to the left. Now the next key goes in the middle because it's between the two, but now we have a problem. Now we have 3 keys in the same node. This is not allowed, so we need to split it. And what we do is we take the middle element and pull it up, and then everything to the left of the middle element gets its own node, and everything to the right gets its own node. So afterwards, it will look like this. And then we continue. So we always try to put the new keys into leaves first. So 4 goes here. 7 goes there. Same problem, we need to split. So we take the middle element and pull it up. It joins the 2, and we get this. 5 goes there, 9 goes there. 8, we need to split again. But this time we also need to split the parent because it's 2 full. So we pull the 6, which is the middle element, up again, and we get this. And then finally, one more split, we obtain this tree. Okay, so this is the insertion algorithm. And for most of this talk, we're not actually interested in what the exact keys are. They're sort of interchangeable. So we represent them by blobs. And by doing this, you lose some information. So for example, here, you cannot tell anymore whether it was the left key or the right key that came from T1. So it's unclear, yeah? But such a sequence of B-trees that sort of, where you don't see the exact values of the keys, we call this a history. And we have this fancy H to denote the set of all histories for B-trees of order 2m plus 1 that contain n keys. Yeah.
So you are dealing only with 2-3 trees, but I assume things work for higher degree.
Yes, and in fact, we'll get slightly back to this in a few slides.
Higher degree, you are assuming that the number of the number of elements in a node is an even number. Otherwise, there's a bias when you split.
Yes.
That isn't so.
Yes.
Okay, and your model is insert only. And we're not going to get into doing deletions.
Correct. We are not deleting anything. I will say the case where you allow for, like, say, 5 as the maximum number of keys in a node, you can modify the bijection. It just gets messy to write everything down. No, you just pick a side. Let's say you always go left or something.
Oh.
It's the idea still works. It just gets more complicated to write it down.
Okay, thanks. I did that.
Okay, so then I've explained what B-trees are. So let me state that there is a bijection between these histories of B-trees and certain increasing trees that have the following properties. So we have rooted plane trees on n vertices, labeled by, well, the first n positive integers. The labeling is increasing. And we only have branchings in 2 further paths at very certain heights. So let me show you how this looks like. So on the left, we see the same history of the B tree again. On the right, we construct the historic tree from the bijection with it. And the actual tree are the gray nodes. The white nodes are sort of to show what the next steps could be. So these are external vertices, if you like. Okay, we have this. And you see that now this is the first time where in the B tree, the new key would have 2 choices. It could go either to the left or to the right. And it's the first time where you have 2 possible choices to continue the increasing tree. Okay, we continue. We put the new key to the right. So we put the new vertex to the right. Here, this is maybe a little bit, I mean, if you compare this B tree versus the next one, then you see that, okay, the new key went into the right of the 2 in the previous step. Yeah, so the new key went here. So we append also on the right. And now we have 3 choices, and we indeed have 3 external vertices. And in this way, you continue. Until you're done. So this is the historic tree, and you've also already seen how the bijection works. You basically say, well, in my history, in what leaf from the left did the new key arrive? And then you append a vertex in the position of the 8th of the according external.
Could you go slowly for the double split?
Yes.
Yeah, there.
Here. Yeah, so let's see. Right, the double split happened here. Yeah. So I insert it here. And that's all that happens. Okay. Yeah? Okay. So I think it's somewhat clear that if you do this construction and it actually works, so you can make sure that the number of leaves for the B tree is always equal to the number of external vertices here, then it's also clear that it will be a bijection. And indeed, we have this proposition that collects some information about what the bijection does. So notably, the first item here says exactly that this is the case. But in order to prove this, you basically keep track of everything. So in particular, you need to keep track about how far you are from the last branching in the historic tree. And it turns out that if you have there are a number of internal vertices in between the external vertex and the branching, then this corresponds to the number of keys in the corresponding leaf of the B tree. Okay, so here this is not so interesting. All the keys contain the bare minimum, all the leaves contain the bare minimum of keys. and all the paths have length, well, have 0 internal vertices on them. So what you have in here is m plus 0. But if we go back one step, then you see that you have this thing where you have m plus 1 keys in the node. And here you have, in the corresponding position, 1 internal node on the path. Okay. So a quick consequence, you can ask, well, since our key sequence was a permutation, what is the set of all the permutations that yield the history? And we'll answer this later. But for now, I'll just say we have this formula, which just counts the number of permutations that give a certain history. And we can use these increasing trees to look at some analytic combinatorics, as we saw yesterday a lot. So that's a bit convenient to remove a little bit from the top of the tree. It's just so that the recursion gets a little bit nicer. It doesn't matter for the counting at all, though. And so these reduced historic trees, I can write down the exponential generating function. And then get, for example, this recursion. The idea is that after the reduction, if I remove the top m vertices, I just have 2 labeled copies of a reduced historic tree. So this is where this equation comes from. And then this is just, well, counting how many possibilities you had for what you cut away. The general case looks like this. And as it turns out, this equation has already been analyzed by, I think, some people in the audience here. But yeah, we can use singularity analysis to derive this asymptotic result. And basically, this has already been done in a different combinatorial context. So for general M, it's more complicated. So the differential equation isn't explicitly solvable anymore. However, we can, if we assume that the same behavior happens, so we have a dominant singularity at some value rho m, then you would get this sort of asymptotics, and it's a conjecture in the paper that this is actually true. It's open. So yes, some numerical computations that Stefan did. So okay, you can also then weigh historic trees, because as we saw a few slides ago, you lose some information by going from the actual keys to the history. So if you account for this and weigh your historic tree by the number of permutations that produce it, then in the case for m equals 1, you get this differential equation, which is actually much nicer to solve. You see this. This is not so surprising because, of course, if you go through all of the histories of n and add together the number of permutations, you should get n factorial. But you can now also keep track of the number of external vertices. And it's, as we saw, the number of leaves in the B tree. And then you get a bivariate exponential generating function. And you can use usual tools to derive a central limit theorem. This result isn't new. It was obtained by Yao in 1978, I want to say. But at least, yeah, it's a new way of getting to the same result. Okay. But let's look on. And let's actually ask, how can we get this set of permutations? So either for a fixed B tree or for a fixed history. And the principal idea is that, well, if my B tree has height 0, so it's only a single vertex, then any permutation works. And if I now can somehow recurse over the height of the tree, then that might work. So what makes me optimistic that this could work? Well, if you take a history like this, and you just imagine that you cut off all the leaves, then you get this. And if you now look at the times where things change, so here, 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 then this looks just like another history. And I should say that this is a combinatorial statement, not a probabilistic one. So as sort of stochastic processes, these behave completely different. And in particular, there is some permutation pi1 that produced this history. And the idea is essentially that, well, if we know this pi1 from the previous step of our recursion, then hopefully we can extend this to regain the set of permutations that had this pi1. As a minor side fact, we can actually obtain pi1 from the full history of T. So this is not enough. But if I see this, then I can basically at every step perform in-order traversals and keep track of which keys went up and then update this accordingly. And this gives me the pi1. Okay, so let's say here, this is the actual pi1 we would get from the history we had. So we have this permutation. Okay, so we need 3 steps. First, this pi1 is a permutation on the number of elements that are in the pruned version of Tn. So we need to lift this permutation to just a sequence of the actual keys in T. That will be easy. Then given the B tree that we want to have and this pi1, we want to produce a historic tree such that, well, the history after pruning fits with this pi1. And then finally, given all of this information, so the T, the historic tree, and this key sequence from step 1, we want to produce a pi that's inside the set. And I should say, as I will go through this, I'm going to make some arbitrary choices, and they will lead to, well, a permutation that gave me the tree. If you make different choices, you get different permutations. And one of the results in the paper is that if you do all possible choices, you get exactly all the, well, you get the entire set. Okay. Okay, so step 1, we have this pi1, we have this B tree. Well, if you just perform in-order traversal, you see that 1 will be, well, this key, so it's in position 2. So this one is actually a 2, and similar for all the other keys. So this permutation becomes this sequence. That was easy. So step 2 is a bit weird, maybe. You build a binary search tree from the pi1, and then you stretch it into a historic tree. But you keep track of the insertion order that you had into the binary tree. So these are the red arrows here. And also, if you remember earlier how I made this comment about the leaves of the B tree tell you how long these distances between the branches and the external vertices are, you need to use this here to actually know how far these external vertices are away from the next branching. Okay, and now finally you delete all labels. Okay, the claim is that this is an acyclic digraph. Any topological labeling of G, which exists because it's acyclic, when I forget about the red arrows, I will have a historic tree. So it gives you a historic tree. And these historic trees that I obtain in this method are in bijection with those histories of the given B tree that have exactly the right pi1. Yeah, so we choose the labeling we've already seen earlier. So it's this one. And now we can perform step 3, right? So we have this data given. R is, well, the range of the keys that I want to sort into the permutation that I want to obtain. And basically at first I look at these 3 vertices. They correspond to the first 3 entries in the permutation. And what I'm going to say is, well, the 2 must be in there, and there must be one smaller and one larger element, and I can assign them arbitrarily. So at first I get some larger element and a smaller element, and then a 2. Up to this, it's choice. And then all of the following entries were on the right-hand side of this first branching. So they will be large elements. Okay, now I can split my range and my permutation. So pi minus contains all the small elements, pi plus contains all the large elements. For R minus, there's nothing to do. I can just write the 1 in here and then copy it in here. So I fix that position. For pi plus, I now need to update the historic tree. I've taken care of these 3 vertices. One of these vertices, I don't know which one, is still large. So I keep that around and I relabel the new age. This is essentially the right branch from the first, the right branch of the historic tree, relabeled to preserve the relative order of the entries. And now I do the same thing again. So I have these 7 entries to fill. I pick the first 3. I know that I need to assign 6 to them, 1 smaller element, 1 larger element. Something like this. The remaining 4 entries, well, 4 is on the left, 5 and 6 are on the right, and 7 is on the left again. This once again splits the remaining entries into pi minus for all the smaller entries, pi plus for all the larger entries. And at this point, I can actually just assign them arbitrarily because I have so few keys left that I won't see any difference. So I can do, for example, this. I copy it up here. And then that's the permutation. And if you've been attentive, then this is, of course, the permutation we started with.
You could get many other permutations that get the same thing by using the arbitrary.
Exactly, right. So every time you make these arbitrary choice for the first 3 entries, you can do what you want. Except that, well, I mean, one of the entries, the median entry is fixed from the list up here, but you can permute them as you wish. Okay, let's conclude. So we have this bijection between a certain class of trees and history of B trees. We've seen that it allows us to have, well, new approaches for counting B trees or counting tree statistics. We have this algorithmic description of determining which permutations lead, for example, to a certain B tree. However, B trees are still really hard to deal with. So almost any question that you can ask is open. So yeah, thank you for your attention.
Who is first?
Me.
Oh.
Because okay, hi. Yeah, very nice talk. Is there any hope of, because you study the number of leaves basically in the B tree. Is there any hope of getting the number of nodes 1 level up, 2 levels up, k levels up?
That is a natural question, and we tried this. There's a problem with this. So maybe here. So you know that at these branchings, this is the point where you move keys up from the leaves. The problem is it's not at all clear which branching does what. So, for example, I mean, there's a bit of, if you think about this for a bit, then for example, you know that this one increases the height of the tree, this one doesn't, but then it's not so clear what happens afterwards. So this gets difficult.
So
Possibly you could, but you really need to understand what's going on in the historic tree if you want to use this.
I see. Do you know, just a related question, but still, because I'm thinking about getting to the height.
Yeah.
Because you go one level up geometrically. Do you know anything about the rank of the root?
The rank of the root.
It's very important for the height, huh? Because then you know how you split.
Yeah. No, I don't think so.
Right? Okay. Oh, thanks.
So, well, I was going to ask, and I think you've answered the question, but basically, you've got short trees and tall trees.
Yeah.
And they don't vary much. And I was expecting that random insertions would give you more likely to be a bit shorter than the tallest. I would have thought that. It's kind of like Luke's result on binary search trees, random insertions that you don't get them more than 4.5 natural log, 3 log base 2, very often. But you do not have results. Your results do not imply anything about that.
No. I should also say that, so for 2-3 trees specifically, there's of course Odlyzko's result that was already discussed yesterday. But Odlyzko did basically, he picked a 2-3 tree uniformly at random.
Yeah.
Which is a different distribution than what you get from these things.
2 trees that you get from a uniform insertion. Are there any bits on whether they tend to be on their more likelihood of taller or shorter, even by somebody doing some experiments?
I would think so, but I don't think you can. I'm pretty sure you can get this from this method, because here you really need the history, so you need that it comes from some evolution.
And all hell breaks loose if you do deletions, just as it does with binary search trees.
We haven't even thought about that.
Okay.
So.
I have maybe an easier question, but I think it's still open. So if you go to a picture of a 2-3 tree, so we represent those as binary trees, where the 3 nodes are a little binary tree, either leaning left or leaning right. And what we're interested in is the external path length of that tree or the average search cost in that tree. And it seems like your bijection might give us some insight in that. Because
that's might be possible, yeah.
Yeah, well, if that might be possible, that's a 50-year open problem.
It probably won't work.
It looks like it.